Having a look here at RLC, parallel AC circuits. So it's just a small experiment, show you how to set it up. Here's a variac up there for a supply voltage. I'm going to set that at 23 volts. Those two terminals down the bottom there will be our supply point for the circuit, and we'll also have a look at the waveforms on an oscilloscope there. You can see over the back here I've got channel 1 hooked up to a blue lead, channel 2 to the, channel 1 to the yellow lead, channel 2 to the blue. So that'll just make it easy to connect into the circuit just for a small experiment and demonstration. So we're going to have an RLC circuit eventually, parallel. We'll just see what happens first up with an RL circuit, a resistor and an inductor in parallel. So I've just used the 390 ohm resistor in parallel with an inductor there, the L, represented by this old fluorescent light ballast there. They'll be in parallel, and the return with a lead, black lead there, so that'll be our return for each. Neutral back to the supply. Just going to take it through a dropping resistor so we can look at the oscilloscope current waveform, and they'll come back to the supply point on our voltmeter there that we'll have set at 23 volts. So active got to come in too from the supply into our parallel branch, which is that. So I'll just bring it into R over here, and so that lead there will be the supply point. We can monitor the circuit current with an ammeter. This little tong tester will do the trick there. So that one there is going to measure, we've got 77 milliamps flowing through the circuit as the total circuit current, and we can see that down there going into the resistor, the 390 ohm resistor down here, there's 58 milliamps going into that one. The inductor, we can tong that one as well going into the inductor, and we're seeing there's 45 milliamps going into the inductor. So you can just see there that 45 plus 58 doesn't equal 77 because of the phase shifts that occur. So if I plug in channel 1 and channel 2 of the oscilloscope, we can have a look and see the waveforms up there on the oscilloscope ready to measure, and there's our two waveforms. So I'll just adjust them so that we can see the phase shift between the two, which is seen there on that screen. Just bring it down a bit so I can sort of roughly see between the peaks of the waveform there. There's a small phase difference between the two. So if we put a capacitor in series, in parallel with the R and L circuit, we'll see this power factor improve. So just down on the panel, I'm going to put a 3.3 microfarad capacitor there in parallel with the rest of the circuit, and the return side, of course, back to our neutral. And just from that little demonstration there over here, we can see that the circuit current has dropped to 66 milliamps. Still 58 milliamps through the resistor, still 45 through the inductor. But if we look at the current through the capacitor, it's drawing 23 milliamps. So there's like more branch currents, but the actual overall circuit current has dropped in that regard because of power factor improvement. So when we look at the oscilloscope, we can see the waveforms have come closer into phase. If I open circuit, the capacitor, see how they jump apart, and there's a higher power factor there with the capacitor, without the capacitor. Circuit current with the capacitor is this one over here, 66 milliamps. Without the capacitor, it's 77 milliamps. So the capacitor adds to power factor improvement. It allows for less current being drawn from the supply and a more in-phase waveform between the voltage and current in the circuit. Yeah, so that's briefly it. That's how you can experiment with power factor correction.